All right. In this video, what I like to do is go through the concepts behind bending reinforcement. I think I said at the start of the last video I was going to do it within that video, but it took me 10 minutes to get through those other concepts, so I decided to split it and make it its own video. So, generally speaking, we're going to start with beam design, and we're going to consider bending reinforcement as far as beams are concerned. When you're doing beam design with reinforced concrete, you've got to think about the same features that we've been dealing with all along. We typically start with bending, then we're going to check our shear and make sure that our deflection doesn't exceed some tolerable limit that we've defined. And for timber, for steel, we've actually sized the beam for bending and then just checked shear and deflection. But with reinforced concrete, we do it different. Because we're dealing with rebar embedded within concrete, we actually have to consider the entire shear and moment diagram all the way along there. And so let's make a note there. This is an important concept. Consider the entire shear and moment diagram. And we'll highlight that red because that's important. All right, what that means for us is we've got to look at essentially what the shear and moment are doing across the entire length of the beam as opposed to just the maximum, which is what we've done before. All right, what I want to do as we start this is just generically think about how beams can be deflected. We'll start with a simply supported beam with a point load in the middle, and we'll go ahead and add some supports out here. And what I'd like to do is just cut that beam right there, halfway between the reaction support and the point load acting in the middle. And if I was to take and we'll blow that beam up just a little bit so we can see it better. Exaggerated this piece of the beam right here. We've still got the reaction out here. To make sure that this part of the beam is in equilibrium, we know that there would be a shear force acting internally within the beam. And of course that's simply that external load, external point load acting middle that's causing shear forces and stresses to develop all the way through the beam until we get out here to the support reaction. The other thing that I want you to note, for this thing to be in equilibrium, it would want to spin right here. We also note that as the beam starts to sag, that it will develop bending stresses along the top and bottom edges. And so along the top edge we'd end up with compression, and along the bottom edge we'd end up with tension. And if we were to draw a cross section of this beam, now we're actually taking a slice of that beam. It could actually be right where we've cut it, and we've turned it sideways now so we can see inside. We'll note that there's some sort of a neutral axis acting along, typically around the center of the member, and everything along this top edge will be in compression, and everything along the bottom will be in tension. Now here's the deal. With reinforced concrete, concrete is great in compression, and so the concrete itself can handle that load along the top. However, in the bottom, concrete is not good in tension, and so we actually run rebar down the bottom of the beam, essentially where we have negative bending, and I'm going to draw two pieces of rebar running through the length of the beam in our cross section, and we note that this is where the tension force is being carried. does concrete have some sort of compression? Sorry, I said that wrong. Does concrete have some sort of a tensile capacity? Yeah, it actually does, but because it's not very much, we actually just neglect it. We just ignore the tension capacity the concrete has and assume that all the tension will have to be carried by the reinforcement. Like, what I like to do next is quickly draw what the stress distribution would look like along this profile. We've defined profile views for stress distribution for steel and for timber, and generically for bending and shear. If we have a moderate, this line just represents the profile or the edge of the cross section there. And we'll go ahead and we'll add a neutral axis right here in the middle. We know that the bending stress along that top edge will look like this. And for our previous elements, the bending stress looked like this along the bottom. But because we're dealing with, try to erase that, because we're dealing with reinforced concrete here, material that can't handle that, the compression zone is fine, but all of the tension has to be carried by a single force, essentially acting through the rebar. And for moderately loaded beams, this theory holds true. However, as we start to approach high loaded beams, the diagram doesn't quite behave as well as the theory that we've talked about would suggest. So here's our neutral axis again. What starts to happen is, rather than that true triangular load, we start to get this kind of curved load that behaves up here at the top. And of course there we've got our tension zone down there. This distance right here from top to bottom of the beam is the H, or the height of the beam. As I've sort of indicated in other lessons, generally speaking, when we have curve type shapes, they become difficult to explain mathematically, and so we try to simplify those as best as possible. So we'll keep our neutral axis here in the middle. And if we could approximate this same area that exists in the compression zone for a high load, and do that as a rectangular shape, that would make life a lot easier. And so we do. Now notice I'm not going as far down as the neutral axis this time, because I'm trying to maintain that zone that exists, in other words, the same area that exists up there. We'll go ahead and throw our rebar back down here. Here's the two design parameters that develop for reinforced concrete. From the top of the beam to the depth of the rebar. Notice I didn't go all the way to the bottom of the beam, I just went to the depth of the rebar, essentially the center line of the rebar. That's called the D, I assume, for depth. The height of the compression block is called A, and that shows up as far as that height is concerned. As far as the magnitude of the compression block, over here we know the maximum would be our compressive stress. There are some adjustments in there, so it usually has this little apostrophe on the end of it. But because we're using an LRFD approach, that's again where we take the failure mechanism and we lower that value some. The phi value for reinforced concrete is 0.85. And so we're going to reduce the magnitude of the compression stress by 80, or not reduce it, but we're going to multiply it by a factor of 85, reduce it by 15%. And so that becomes the magnitude of that compression block. So if you were to calculate the area of this up here, we'd have a value of A as a height and 0.85 times F prime C as our width. Now, we would also note that there, going into the page, this beam has a width, and the width of the beam is B. Width of beam B. All right, what does this mean for calculating the moments and making sure that everything stays in equilibrium? At a practical tension limit, in other words, using the full capacity of the materials, the tensile force, by the way, I didn't note this earlier. I'm gonna do it with a green arrow here. We could come up with our equilibrium vector that represents that distributed load, and that would of course be a value of C, and of course our tension would be a value of T down here. All right, at that practical limit, the tensile load, I'm going to go back and erase this. It looks like a lowercase t, but I want it to be a capital T. There we go. The tensile limit, or in other words, the strength of the steel, is a function of the area of the steel times the yield strength of the steel. So area of steel and the yield strength of the steel. That means that we're trying to keep everything within the elastic range of the steel. That would be the tension force. The compressive force, on the other hand, is simply a function of the volume of that block. The area is what gives us, as I've notated here, gives us that resultant force acting at the center of the distributed load, and then we'd simply multiply that by the beam width. Essentially, we're getting a volume of that compressive stress block. So C equals the magnitude of the stress. Whoops, that did not work right. F prime C, I put FC prime. That's the magnitude or the width of that block, and we multiply it by the height of the compression block, and we multiply it by the width of the beam. That's going into the page. So if I had a looking at this diagram right here, if this particular beam was 20 inches tall and 10 inches wide, we'd be looking at a B value of 10 inches. Just to make up some numbers right there. All right, here's the crux of the theory right here. If we were to balance this, we want to keep everything in equilibrium at the practical stress limits. We would know that the tension and compression would have to be equal to each other. We could set those equal to each other. And here's the cool part right here. If I solved for the area of the steel, essentially, this is the value that I want to solve to find out how much steel I need. I've already given you a table that you can calculate the percentage of steel needed for a balanced section. But here's the deal. A balanced section is not practical for design, we often use what we call an underbalanced section. In other words, we actually can use less reinforcement than required for a balanced moment. Now we have to adjust where it remains in the profile. That's essentially the D value right there. And also what that does is that changes our compression block a little bit. But by using a slightly lesser amount of steel, we're able to save money. And so this equation right here is a way of solving the A value because we don't know what it is. We've drawn it on there conceptually, but we actually have to solve for that. And this is the process of doing reinforced concrete design. If we don't know what that A value is, we don't know what that D value is, then we've got to do an iterative process where we figure that out. I used to have the students go through a calculation where they would run this. I've stopped doing that as of a semester or two ago. I'm trying to focus mostly on the concepts here. And so generally speaking, you won't actually have to use this A value for anything other than I wanted you to recognize that conceptually speaking, what we're solving for here is this compressive stress block that develops at the top section of our beam. And that's how we decide how much rebar we actually need. Now, two quick things to note. There are a few minimum values that have to be met. One value that has to be met typically is, let's do our spacing. How far apart could our bars be? Typical minimum values are 1 bar diameter or 1 inch. This is diameter right there. That's a period. 1 bar diameter or 1 inch. There's also a couple equations that govern the minimum amount of steel. Rather than give you the equations, what I just want to note is that we typically have to check and ensure, even if the beam doesn't have a large bending load, we still have to check for temperature and shrinkage. That is how the concrete expands and contracts with regard to increases in temperature in the summer and decreases in temperature in the wintertime. And we have to make sure that the amount of steel embedded within the concrete accounts for that. So there's also a minimum value of temperature and shrinkage steel that has to be kept. All right, what does all this mean? Let's draw a couple diagrams here and show you what tension reinforcement means. And then I'm going to show you how we would actually draw that inside of a beam. Remember earlier I said that we have to consider the full moment diagram. So I'm going to draw a standard moment diagram right here for a simple span. This would be a simply supported beam. This is the moment diagram since we're dealing with bending stress, we're dealing with the bending moment. And if we put a beam right under this, right here, you'll note that at the outer edges, the bending is 0. So in theory, we don't need any reinforcement out there. The bending is maximum at the center of the beam. And what that means, I like to draw my reinforcement green. I don't know if you caught that earlier. I worked for the state DOT and all our rebar was epoxy coated with green epoxy. So I just always draw it green in the class. What that means is that we need to have our rebar at the bottom edge where with positive bending, I actually think I said negative bending earlier. It should be positive bending. Positive bending will cause tension in the bottom of the beam because of the way it sags. The bottom of the beam will go into tension, so we need to make sure that our rebar is in the bottom of the beam in the tension zone. And occasionally what you'll see is if the moment is really big in the middle, sometimes they'll actually throw in an extra layer of rebar towards the center of the beam where that bending is even a little bigger. So sometimes you'll see them change where the rebar, or the amount of rebar that's in a beam. If we consider a continuous span, again, I'll draw the moment diagram for you here. Maybe it'd be easier if we drew the beam first. I'm only going to draw that much of the beam for now because I've got another thing I want to show you with it. Well, actually, we'll do the whole thing. It's quite common to see what we call a T-beam, where we've got these, acts like a beam towards the center, even though it's all poured in one pour. We've got these essentially stiffeners that hang down, act as a beam support in the center of the slab. If we were to go and look at our 3-span slab for the moment diagram, if you recall, what we'd end up with is everywhere we've got a support, we would have negative bending because it's a continuous beam. And at the center of all of these slabs, we'd have positive bending. And if we connect the dots, you'll recall seeing this in our common shape solutions, we end up with something that looks like this. Now note, I've got negative bending that transitions to positive bending, that transitions to negative bending, etc., all the way across. And anywhere that we've got positive bending, we know that we're going to need rebar in the tension zone, which is at the bottom of the beam. And anywhere where we've got negative bending, the tension zone will be at the top of the beam. And so we would actually need rebar in these zones right here. Now often the edges end up getting wrapped. We'll talk about that in another video. But these would be the locations of the minimum amount of bending for negative moments in the top and for positive moments in the bottom. Now, has anybody ever seen a beam that only has this much rebar in it? No. What I'm showing here on the diagram is the minimum amount of rebar needed for bending. Again, speaking of the tension zones. But when we go back to this idea that I mentioned a moment ago, where we've got temperature shrinkage still needed as well, what would happen is we'd end up having a complete rebar cage that would account for temperature and shrinkage still as well. So what you might end up with is some smaller pieces of rebar throughout other parts of the cage, but with bigger pieces of rebar in these zones that are a little more critical.